So, thank you very much for the introduction and to the organizers for inviting me to this beautiful place. And being on the road of thanking, I would to thank my collaborators in this work. So, most of the graphs I will present are from Bernd Eichner's PhD thesis, additional material from the thesis of Lukas Backmeister and Philip Korner. We had some help from Barbara Budinska, who is a PhD student from Alexander, and the samples were prepared by Max Kara, Katja Wulster from Dieter Kölles group in Tübingen. Well, it's working. I'm lucky. So, thank you for the techniques. This diagram is well known to everybody in the audience. I need not mention more, except maybe that the vortex state in the copper oxide superconductors is much more extended that you see in this textbook graph. So Meissner state is very little, and there is a huge upper critical field. So whatever you do, practically you are mostly in this vortex state where the vortexes penetrates into the superconductor, and for technical applications, you usually do not like this. So many concepts of pinnings have been explored for technical applications like tapes and so on, usually by introducing arbitrarily distributed defects, either during the fabrication by nano-inclusions or by irradiation with swift heavy ions, for instance. So producing pinning is quite a common topic from the very beginning of the research in copper oxide superconductors. But there is another thing which could be interesting, which is explore pinning of regular patterns, so that you can design any pattern you would like to have. And this cannot be done by these previous methods because they have some arbitrary distribution of pinning centers. And for all of these pinning explorations, there is one condition which is important. The distance of the pinning sites should be smaller than the London penetration depths, and you can hardly reach this in classical superconductors like in niobium. You need to go down to like 40 nanometers, and in typical high-Tcis superconductors like YBCO, you would need like 150 nanometers, which is kind of far below what you can do with conventional lithography. So there are several types of defects you can introduce, and I would like to introduce you to the Vienna Zoo, which is the oldest one in the world. So sorry for this product placement here, but we can use several kind of animals for explaining the different pinning sites. So the hexagonal lattice, as you see it in a turtle, is the state which you have in a clean superconductor. It's quite well known. It might even have some little distortion, but this is quite common. If you introduce point defects, you have something like the cheetah. Random point defects can be either intrinsically by atomic displacements or lack of some atoms, interstitials, and so on, or you can introduce them by soft irradiation, like electron irradiation, proton irradiation, light ion irradiation, and so on. And this gives typical way of pinning the vortices in an entangled form, which we will discuss later on. Another thing is the tiger, which has kind of kind of one-dimensional segments of pinning sites. This typically can be introduced by self-assembling of defects like this barium zirconium nanorods, where you have pinning sites which are one-dimensional but do not extend over the entire sample. And the next step in progress would be the antelope, where you have these pinning sites over the entire depth of the sample, but still arbitrarily distributed. This is what you have when you irradiate with swift heavy ions, for instance. And these are the defect tracks you create with the ions. But what we want to achieve is something like in the emperor's anglefish, a pattern which goes through the entire sample and is equally spaced, so is regular. But unfortunately, in all these attempts, we might end up in something like a tapir, which means we have some of these extended one-dimensional defects, but in addition, we have some point defects in between. So this will be kind of layout of my talk. Well, Alejandro has already mentioned the delicate structure of YBCO. So I come from another point, so I do not use high electric fields and currents, but basically the thing is the same. This copper oxide chain oxygen atoms are very weakly bound by 1 or 2 electron volts, can be easily kicked around, also by irradiation. And this can be done, for instance, by a focused helium ion beam, so a little bit similar than Rosa told us. We use a helium ion beam, which we can scan over the surface and blank it, and by that we can, in principle, program any arbitrary pattern which we like to see. This is more or less equivalent to a superconductor with holes, not exactly, but more or less. And if we apply a magnetic field perpendicular to the surface, we can find a particular field called the matching field, where a flux quantum penetrates every hole, or in our defect nanopillar in our case. And there is a easily to calculate field where this matching or commensurability should occur, which is just given by the area of this defect lattice and the flux quantum. Now the instrument we use is a helium ion microscope, which we use in a kind of modified fashion. It's built for making pictures. We force it to destroy samples, which is a little bit different. So rather intense ion beam is focused on the sample surface, and contrary to the original design, which is a very sharp beam, like 0.5 nanometer diameter, we widen it up a little bit because this is more favorable to get a more homogeneous kind of nanopillar in our system. What we can achieve, for instance, this is a picture of 20 nanometer spaced hexagonal lattice of such nanopillars viewed from the top. And actually our samples, where we'll present the measurements later on, do not look like that. So we have exaggerated the fluence very much to visualize. So these are essentially blisters. So we really destroy the sample here. In original samples which we use for measurements, you don't see anything, because we just kick around oxygen atoms, mainly oxygen atoms, and do not destroy the crystallographic framework of the entire structure, so it's not visible. And from a side view, it looks like that. If the dose of ions is rather low, you don't see anything. If it's a little bit higher, you see emerging of one of these nanopillars. If it's even still higher, you see an amorphized zone of about 7 nanometer, which means the stronger you hit the sample, the wider is this pillar. But this is with focused, strictly focused ion beam, and when we widen it up a little bit, we come to this situation here, where we don't see anything, but still have the effect on the transport properties. But we should understand a little bit what's going on in transport, and for that, we irradiated samples flatly, which means without any particular structures, just by overlapping the beam, very widened up beam and overlapping, so it's a homogeneous fluence over the surface of the sample. And we see resistance, so Tc goes down, obviously, resistance goes up, and there is one kind of common knowledge how to interpret such resistivity curves, and this is that the slope more or less corresponds to the inverse carrier concentration, and the offset corresponds to the number of defects you have in the sample. So essentially, the oxygen content is not changed at reasonably low fluencies, but defects go up, and the same finding you can also see in the Hall effect. Nevin has elaborated on the strange Hall effect in YBCO, but we just use it as a simple probe. So here we use the inverse Hall angle, which is a probe, according to Phil Anderson, for both number of carriers and defects. So it's quite a similar formula if you scale it like that. And you see the same. You see essentially the same slope and an increase of the defects. So what we know is we induce a lot of defects with the irradiation, but we do not lose oxygen. We still have fully oxidized YBCO. With this data, we can carry on and try to simulate the three-dimensional structure of these nanopillars. There is well-known software for that, the SRIM trim package, but this gives only the defects per atoms, which you see in this example here. And the defects per atom can be kind of parameterized by experimental data to Tc. And this is just by using what we had before, so taking the resistivity data, taking the onset of Tc, plotting this along the dPA, which we have from simulations, actually from plane field simulations. And then we see this nicely follows the Abrikosov-Gorkov pair breaking theory, which on one hand might be a little bit of a surprise because the theory is for magnetic inclusions, but it's well known that since YBCO is a D-wave superconductor, also elastic scattering on point defects are pair breaking, so it goes with the same Abrikosov-Gorkov law here. And this curve we can now use to calibrate. We can go from a dPA value to the curve and then to a Tc. And using that, we get the structure of our nanopillars. So you see, essentially the red one means Tc is fully suppressed. And the diameter is something a little below 10 nanometers, what we can achieve. This depends a little bit on the fluence that we use, but essentially the trade-off is if we use too high fluence, we have amorphization and wider nanopillars. If we have too low fluence, Tc is not fully suppressed. So it needs some kind of delicate adjustment of the parameters to get where we want. Okay, but nevertheless, we have an idea what's going on from these simulations, and we use them to see what is the limit of this method. So how dense can we make these patterns? And you see some of the simulations here. A 30 nanometer hexagonal lattice, 25, 20, and 15. This is very well developed, as you see. This is a top view, this is a side view where you see these channels. And with the 50 nanometer, obviously, there is no percolation path anymore, which remains superconducting. It's exactly what we see in transport measurements. So we have the different lattices. Some of them have only slightly suppressed Tc, and the 50 nanometer sample is semiconducting. So obviously there it breaks down. So we will focus on the 20 nanometer sample. The fact that Tc is a little reduced is just by the fact that we have some minor defects from straggling of the ion path. So these trajectories are not exactly parallel to the z-axis because there are collisions and there's always straggling a little bit, and we have some minor amount of defects in between, which by the same law as I have shown before also reduce Tc, but fortunately only a little. So with this 20 nanometer spaced lattice, we can measure critical current, and what you see is a peak in critical current at 6 Tesla, which to my knowledge is quite a record high field, because previous works were more or less limited to the range of 10 or 100 of millitesla. And so this is a clear peak in the critical current. It becomes even more obvious if we normalize to this peak. Then you see that at a little bit elevated temperatures, so the color coding is here, maybe at 25 Kelvin, we have a very pronounced peak already. It's just not seen very well here due to the scaling. So obviously, if intrinsic pinning is not that strong at little bit elevated temperature, then this artificial pinning, which we introduced, becomes even more prominent. So one important point is we have this commensurability at very high magnetic fields. These are fields which are typically in previous explorations of arbitrarily distributed defects, like heavy ion irradiation. So these people were in the range of several Tesla of matching field, but they did not see any peaks because it was an arbitrary distribution of the pinning sites. The second part, which is also quite interesting, is that now we can have commensurability effect over the entire transition. So you see here is 2 Kelvin where we see already something, and this goes up to, let's say 55 Kelvin. If I remind you, the Tc onset of this sample was 50 Kelvin. So we see it up almost into the normal state, which means that at the first bending into the superconducting transition, we have not a real vortex liquid, because then it would have no commensurability effect. We have kind of a plastic flow of a vortex ensemble. So this goes up to really high temperatures. Yeah. Then we go back to the 30 nanometer sample, because this had this very nice contrast. It's obviously a little better than the 20 nanometer sample, has a matching field of 2.6 Tesla, and explore the critical current. So critical current there is very remarkably, so this is scaled to the one at B equals 0. And you see it's going up to quite high values. If we take, let's say, 40 Kelvin data, this is the pink curve here, then you see it goes up to 80% at 2.6 Tesla, which is quite remarkable, because we can compare to films. So I took one recent work, which is quite representative for several published works, but they had data exactly also at 40 Kelvin, so I can directly compare. This is the main advantage. And you see at the same field, and where is our matching field, a genuine, so a non-processed YBCO sample has dropped down to 25% of critical current. And even with this BCO nanorods, which is the tiger structure, it comes up to 40%. And if we take just this data and plot it here, you see it looks like that. So at high fields, it rather well matches our curve in our sample, which is the pink one. But in this field, you see this very pronounced peak. At very low fields, our structured sample even fall off a little bit more rapidly. So we would say this is close to this anglefish structure what we have produced here. But we would explore the critical current a little bit further, because critical current is a very diffuse thing. You know, this is a voltage criterion. If you have very good equipment, then you have very bad samples, because you can measure to very low voltages, which reduces the critical current. So critical current rather has to be at least checked or explored also by IV curves. And if we do that in that sample, and actually at the point where we have this maximum critical current, so at the 2.6 Tesla, we see something like that. There was this old question, is a dirty copper oxide superconducting a real superconductor? And it's many years ago when it was raised, and it's longer time ago already solved. But the point was this: if you make these IV curves, take this red one here, then you see there is a ohmic region. It looks a little bit distorted because it's just a projection, so it's strictly linear here in reality. And this is attributed to the well-known thermally assisted flux flow, which means that the temperature is high enough to activate your flux lines, and even at the lowest measuring currents, you have a finite resistance, which means that these lines here, even if you go to extremely good instrumentation, you still can detect resistance, because resistance basically is the same all over here. And this tough regime happens at somewhat higher temperatures. But if you look carefully at such data, and they are not different from data, or they are qualitatively not different from what you have on a plain YBCO film, for instance, without any patterning, so there is a positive curvature. Then it goes over to a negative curvature, and there is some separation line, which is green here, where it's a power law behavior, what you can see here. And the theoretical background also is quite old and very known since long time, which are the vortex glass theories. There are essentially two which are relevant for my talk here. The vortex glass, initially proposed by Fischer, is for zero-dimensional defects or point defects, the cheetah situation. And the Bose glass is for one-dimensional defects. Essentially, this is the situation of the antelope. And both theories predict a very particular scaling, which is this seemingly complicated formula here. But as you see in a second, if you apply this formula just for scaling the axis appropriately, you end up with something like that. So these F are universal functions which are unfortunately look a little bit different here in the view graph, but this should be F plus and F minus. And all this data you see here can be collapsed to two universal curves. And this function F is in principle not known, but is characteristics for a particular glass system. So this is a very genuine and very fundamental theory which does not put anything inside like particular structure or material or something like that. If it's a second order transition, which is a glassy behavior, it should end up that according to this formula, you should be able to scale all this data in the vicinity of the glass temperature. Obviously, there is a validity range as in any second order transition. It is not be valid indefinitely, but you see it's quite a large temperature range which could be collapsed here. And this theory has essentially three parameters. One is this glass temperature, which separates these two branches. And there are a static exponent nu, which essentially tells you the correlation length of the glass or the fluctuations of this glass. And a dynamic parameter, the set, which tells you how it reacts to dynamic excitations, in particular also to alternating current and so on. So we did this many years ago where you can explore the phase and then you see the glass transition also in the phase. But this we don't do here. We just keep with these three parameters. And you see as a comparison, I have now plotted the top two curves are at matching field and the other two are off the matching field. And you see there is a very distinct change in the properties of the system, and particularly this dotted line, the separatrix, which virtually presents the behavior exactly at the glass temperature, is quite different. So you have here I to the fourth and I with an exponent 2.75. So which means if we are in this matching condition, we have a definitely different vortex dynamics than offside this matching condition. Putting these parameters in graphs, here is the behavior of this glass temperature independence of temperature and magnetic field, kind of a phase diagram, which we know from several other things. And this dotted line here is how it looks like in a plane YBCO film. So it's an essentially linear decrease of the glass temperature with the magnetic field. But if we pattern our sample with this particular structure, you see there is a strong bump in this phase transition boundary at the first matching field and also a minor one at the second matching field. Second matching fields means that we have two vortices per unit cell of the defect lattice, but we do not exactly where the second vortex sits. There is the possibility it also sits in the defect, but it's repelled, so we have kind of elastic force on the vortices, or it might sit on an interstitial position. So we cannot ultimately clarify this at the very moment, but obviously it's another form of commensurability as well. Good. Taking these parameters, now this nu, as I mentioned before, the correlation length is very insensitive. Both in theories and also in experiments, we see there is no particular feature as our matching fields, but the dynamic parameter, which characterize essentially the movement of vortices, has a very pronounced peak exactly at the matching, which we would attribute to the fish scenario. I should mention the theory predicts both for vortex and Bose classes. Interestingly, both of the theories are from the concept are substantially different. They come to very similar critical exponents. So from these data, it's not possible to discriminate between a vortex or a Bose class. So means zero-dimensional or one-dimensional pinning. This would be this gray area, so between cheetah and antelope, basically this can be discriminated by angle resolved measurements, which we did with some other samples before, so we are pretty sure it's a Bose class, and this is very natural. But going back, this peak goes very much outside of this validity range from the theory. And the theory is made for arbitrary defects, not for regularly spaced defects. On the other hand, we know if we have a first order transition and a sharp melting of actually a lattice, would be then a vortex Mott insulator, and I think we will hear more about vortex Mott insulators later, then this set should essentially go to infinity, which means a higher set is an indication of a higher degree of ordering. So this is here, and if we tune the magnetic field of the matching condition, we, oops, oh, I did a mistake or not. Oh, but I did not press this dangerous button. Okay, oops. Back. Almost have it. Yeah, here. That we have this tapir situation. So we have a mixture of pinned vortices in the defects, and we have some pinning in between. And in these intrinsic defects, we still survive in between. And we want to call this an ordered Bose class, kind of a new observation of a phase in such vortex system. Why ordered Bose class? Because it scales like a Bose class, which means it's not a crystalline lattice of vortices, or it might be a vortex Mott insulator excited to higher temperatures, but also with additional defects in between. But in contrast to a regular Bose class, it has this pronounced peak and this higher, let's say, steepness of the transition at the matching condition. So I think my time is almost over. So just to mention that you can use this technique as well to produce other lattices, like a quasi-Kagome lattice, where you can explore competition between elastic energy of the vortex lattice which wants to restore the hexagonal lattice and a distorted one. And these are some older results, so I have presented them before. And essentially, I come to my conclusions that with the helium-ion microscope, you can produce nanopillars in YBCO films on a very dense scale, which you can use for playing around with different vortex matching effects. So one we have demonstrated is matching at 6 Tesla, and the other thing which we found and which we propose to call it an ordered Bose class when we have pinned vortices in an hexagonal lattice plus intrinsic defects in between. Thank you very much for your attention.
The presentation is open for questions.
So I have a question concerning the first part, YBCO with you grow it on top of STO or?
No, it's LSAT, lanthanum aluminum.
And do you know if the helium goes through, reach the substrate?
It definitely goes through, at least from simulations.
Yeah.
And this is the idea, because we want to have the defects penetrating our entire YBCO field.
But how much it modifies the substrate? Because I guess that
much less than the YBCO, because the substrate is more rigid in some sense. It does not have this movable archisense. But if we amorphize the YBCO, then we see some growing of the crystal lattice of the substrate as well. It's not what we do for the experiments, but Dieter had made some, or actually not Dieter, but we have some data on transverse high resolution TEM, where it's irradiated by far too high fluence, and then we see the YBCO is blowing up, and also the substrate is deformed a little bit.
I wonder if it's not possible to irradiate first the substrate and then grow the YBCO, because I will change the property of YBCO as well in a more columnar way, and that can go much higher, much more than the range of the penetration of the...
Yeah, sure, you're right. So this would be kind of a templating strategy.
Yeah, right.
Might be done.
Any further questions, please?
It might be a silly question, but have you considered strain effects on the crystal, or is it completely irrelevant?
For transport is rather irrelevant, but we are sure that strange effects are there. So there is no doubt. We know from plane irradiation where we have X-ray data that, for instance, the Z-axis distance expands a little bit due to reshuffling the oxygen from their chain positions to some interstitial positions, and this expands a little bit. But I guess it would relax in a few elementary cells with, but it doesn't pose any problem for us. If it is too strong, it would just reduce our transport, so the Tc in between these nanopillars.
Okay, I think we have no more time. Would you like, please?
Very quick one.
Very
Do you,
quick one.
since Dieter Reinhold, big expert of green managers and junctions, have you ever thought of if to please these defects would improve the quality of your junction by crystallographic junctions?
Actually, something Dieter and me have already on the radar,
Okay.
because we can evacuate it, flux, and all these
Yeah,
concepts.
you've been and
Good. Now I have the pleasure to invite my co-chair, David Massaroli, to introduce himself.
Thank you very much.